So we're going to talk about strange things that particles do when they cluster. So first of all, we rely on clustering. We need clustering for many, many reasons. For example, planet formation from planetesimals is due to clustering of dust particles, which become pebbles and then bigger and bigger objects as they come together and cluster. Raindrops, it will never rain if raindrops didn't cluster, and we need rain. Marine snow, like plankton in the ocean, need to cluster as they go down, and that's the way that carbon is drawn deep into the ocean. And for other things like reproduction and communication, you need this. So we will define clustering as places where del dot v is the particle velocity field. Wherever that is less than 0, you have clustering. So more things are coming in than going out. So that's del dot v less than 0. So this is a standard dogma which many of you would have seen all the time. Whenever there are inertial particles in turbulence or in any flow, so if the particle has a response time tau and the flow has a response time t, if tau is kind of significant, like the Stokes number is greater than 0, then particles tend to cluster. And how do they do it? They leave regions of vorticity and they cluster into regions of strain. So think of this as a region of strain, and all particles are coming into it and they cluster along these lines. Whereas if you have a closed streamline, then things get evacuated out of it. There is this Okubo-Weiss parameter, which is vorticity magnitude square minus strain magnitude square. This is high strain, high vorticity. And wherever this thing is positive, you have evacuation. So del dot V is, it can be shown at small Stokes that del dot V is Stokes times Q. So the moral here is, whenever you have closed streamlines, particles evacuate. Whenever you have saddles, particles collect in that and cluster like crazy. So if you want planetesimals to form or whatever, you need this. And I'm referring to caustics as extreme clustering, where particles actually come and dash on each other. So this is like a homogeneous distribution of particles. These are clusters. Wherever there's like lots of clustering, del dot V is less than 0. Wherever there's evacuation, del dot V is greater than 0. And caustic events are where they're actually dashing. So it's extreme level of clustering with del dot V tending to minus infinity. And the point is that suppose you started in a 3D space, they'll go to a smaller dimensional space. So particles are actually going to occupy smaller dimensions than the dimension in which they live in. Okay, so we're going to talk, this is the dogma. We're going to talk about 4 cases of strange clustering. So strange clustering 1. If you have one vortex, we agreed that it evacuates from the vortex. What if you have 2 vortices? It should just evacuate the region of both the vortices and go out, right? No. Suppose these are the 2 vortices. Every particle which started out in this black regime, in this particular example, actually goes to a strange attractor. It goes to a chaotic attractor. So everything that started there is actually going to occupy less than 2 dimensions. We're living in 2D, and it's going to occupy this strange attractor. And notice that these are closed streamlines in the rotating frame. So we agreed that closed streamlines means there'll be evacuation. But no, things which are starting in kind of closed streamlines are actually going into chaotic attractors. They can go into points, they can go into other limit cycles of all kinds. I've just shown one example here. Strange clustering 2nd. Active particles with no inertia. So the Stokes number is 0. So these particles should just go round and round and round whenever you have a vortex, and they should not cluster, they should not do anything. But here's what they do. So it kind of looks like, inertial particles, and active particles do this because they have some kind of reluctance to turn and follow the flow. So although their Stokes number is 0, their orientation provides a time scale which kind of behaves like a Stokes number, but there are important differences. In particular, they don't cluster in strain regions. They leave vertical regions but don't always cluster in strain regions. So this is another thing which actually clusters without inertia. So it's strange clustering 2nd. Strange clustering 3rd. This one is not strange. So these are 2. So this is actually done in the lab and theory, like Rahul Chajwa did the lab experiments, and Harshit did the theoretical thing for this. So like this is a line of ellipsoids, and these are now interacting hydrodynamically. And this part is well known, that these, spheres and things will cluster like this when you let them go under gravity. So you just start them in a straight line and you have clustering here at the valleys of the perturbation. But we get some interesting kind of non-clustering behavior in ellipsoids, where instead of clustering at the valleys, they will kind of pair up and they'll form T. They'll form an inverted T. See here, lots of inverted T's, and we have a story for why that happens. And this is a case of suppressed clustering due to the shape interaction, like the way ellipsoids turn away from each other. That kind of makes this clustering. And the last clustering I want to tell you is about when you have caustics. So we looked at the dogma that they will leave the vortex region and they will cluster into the strain region. So actually they should be clustering on that line and that line. And instead of that, here is the place where there is the maximum strain. And then they don't cluster there. They wait for some time. They go to a place which is not so strained and they form caustics there. They go and dash there. And this can actually be got analytically, this caustics thing. That's the interesting part of this. So like they're actually crossing the streamlines and they're forming caustics somewhere else. So basically I want to say that this dogma shouldn't just be believed. There's lots and lots of counter examples. Thanks for your attention.
Time for questions.
This one. The only difference between these two is one is sphere, another is ellipse.
Sorry. Both are ellipsoids, but they're different conditions. In one condition, the separation between them is smaller in that one. In this, the separation between them is bigger. So whenever they're slightly more dilute, it's not quite that, but dilution helps. So that's the only difference in them. That one behaves like spheres behave. Spheres will behave like that even when they're here. But only ellipsoids can do something different. And there is the stability analysis will tell you that it's a kind of neutrally stable situation which can give algebraic growth. This one. That is an unstable situation.
Hi. Thanks, ma'am, for nice talk. I have a question for the strange kind of clustering of second type. So there active particles are there, no inertia, right? So may I know what is the equation, or how the active particles dynamic will look like? I mean, what things are contributing to their dynamics? Yeah.
Okay, I didn't put the equations deliberately because it's a 10-minute talk.
Yes,
But basically, these particles, they have a size and they have a way they turn and they have an orientation. And the size, like the fluid can stretch them. And if they're longer, then they will orient a certain way and take time to orient. So that there's an extra term there which behaves like a pseudo Stokes number, a pseudo inertia.
Okay, thank you, ma'am.
The first kind of clustering that you talked about, does it matter if the two vortices are like rotating in the same direction or in the opposite direction?
It matters. So like if they're counterclockwise, nothing very fun will happen. So if they're rotating counterclockwise, they will just go in a straight line and nothing much will happen. But if they're co-rotating, even if they're of different strengths, then all this fun stuff will happen. So yeah, like in 2D turbulence, there's a lot of co-rotating vortices which come together to merge. So yeah.
Do you have a picture for strange clustering 4? Do you have a picture for the strange clustering 4, type 4?
I don't have a picture, but it looks similar to
second one.
It looks similar to that first movie I showed you, except that the high strain regions are not where the high clustering is happening. The particles are going past the high strain region and clustering somewhere else.
Nice talk.
that 2D or they have a thickness?
These,
Yeah.
they are 3D printed and they're like little things like this. So they have a little thickness. So they're like a little coin.
So, do you, in your model have you looked at if they are not ellipse, rather in liquid crystal you see banana kind of shapes. So
Okay.
they have a boomerang kind of shape.
Okay, so if you go away from a sphere or an ellipsoid, then like very, very amazing things can happen. I didn't talk about that. So even one particle can do quasi-periodic
So in your
settling.
paper it's already there?
Huh?
In your this paper?
Not
so
in this paper. It's in a PRL which came out 2 months ago.
it's
So
there.
yeah, you can look for these things where instead of an ellipsoid, we removed one symmetry.
Okay.
And we show that it can do amazing kinds of settling.
Good. Thank you.
So yeah.
Yeah, Rama. So in case of non-inertial active particles in the turbulence, you said they have some response time to have alignment.
Yeah.
So does that mean there is moment of inertia rather than the inertia? So is there inertia in the theta term?
No, it's actually not inertia because it's overdamped. There's just a time scale for reorienting and that kind of, so in the sense that suppose there's a particle whose nose is like this and the flow is like that, it's following its nose rather than following the flow. So it's taking time to reorient and follow the flow or get stretched according to the flow. So that kind of behaves like a time delay, but it's not an inertia in any sense. That's what I would say.
So there can be.
Yeah, you can have a kind of, it's a kind of reluctance to follow the flow, basically that.
But isn't that what inertia is? Inertia kinds of
Yes,
introduces a delay.
Yes, yes.
But you're saying there is no inertia in the x or the motion, but in the orientation. So I thought there might be some moment of inertia. I don't. We can discuss.
Yeah, we'll discuss this later.
Yeah.
But like it's a function of how stretched it is, and then it goes back to
So
zero.
if you had a point particle without any length associated to it,
Yeah.
then it would react immediately.
Correct, which is why it doesn't go to the strained regions. It goes out and shrinks.
So, just one question after what the discussion went there, that because of this inertia, is there a possibility that the flow gets perturbed? Is there a possibility of perturbation being introduced because of this strange attractors and the dynamics that's going on?
Correct. So in some of these studies, like we pretended that it's one-way coupling, namely the flow tells the particle what to do, but the particle doesn't tell the flow what to do. But that's not quite correct. When there's a large amount of clustering, in fact, particles can change the flow around them. And this one, for example, it's happening because of that. It's happening because a particle is disturbing the flow. You can describe it in terms of flow streamlines, which are very complicated streamlines around each particle. Yeah, the particles, you describe them, their Lagrangian displacement, but it gives an Eulerian flow perturbation.
Okay, so please thank the speaker for a nice talk.